Hey there, everybody. So for our second week, doing some review as we kind of get a hold on how we're going to continue with our online learning, we're going to spend some time talking about our exponentials and exponential functions today. So before we get into the review, I want to talk a little bit about our formula again. Our formula usually looks something along the lines of this. So we've got a equals p parentheses 1 plus or minus our percent to the t. That answer, or that a, is our final amount. That p is our starting amount. Now again, the letters you use are fairly irrelevant. Then we have our plus and minus. That one's always there. So plus is for growth, minus is for decay. Then we have our percent. Now remember, it's always our percent, and I'm going to star this as a decimal. So remember, something like 3.2% really gets plugged in there as 0.032. We move that decimal point 2 places to the left. And then the last piece, that t, is always our time. It could be in years, it could be in months, depending on the problem. So if we look at our first one here, a high school sponsored a badminton tournament. After each round, 1/2 of the players were eliminated. If there were 64 players at the start of the tournament, which equation models the number of players after 3 rounds? So a couple things here. 1/2 of the players were eliminated. Well, half is really 50%. Left after 3 rounds. Now, normally our time is in days or weeks or something like that, but in this case, 3 rounds represents our time. So that's got to be our exponent. So right there, C and D are out. So now it leaves us with the fact that if players are eliminated, that means we are going to be in a decay function, which means we are going to subtract. Okay? And again, 50% really would be 0.5 or 0.50. So if we need our exponent of 3, we're decaying, so we're subtracting, and 50% is 0.5, then we are going to be with choice A. A laboratory technician used the function T of m equals 2 times 3 to the 2m plus 1 to model her research. Consider the following expressions. Which function is equivalent? The best way to do this, in all honesty, is to plug each of them into your calculator. So if we go to our calculator and go y equals, the first thing I'm going to do is plug in the original, which is 2 parentheses 3 to the 2x plus 1. Now, if I have a newer calculator, it extends itself all the way up there just like I need. If you have an older calculator, then you're going to have to do this. You're going to have, if it doesn't actually give you an exponent, it gives you that little caret symbol, you're going to have to put that 2m, or 2x, I should say, plus 1 into parentheses like that, and then you will be fine. So now I'm going to put this into y2, y3, and y4. Now you could choose to put them all in at the same time. You can put them in separately. It's up to you. So then we are 6 times 3 to the 2x. We are going to be 6 times 6 to the 2x. And then 6 times 9 to the x. And again, anybody with older calculators like this, just make sure your exponent is in parentheses every time, no matter what it is. So now if we look at our calculator tables here, what we want to look at is we want to be able to compare them all. And which ones have exactly the same tables at all time? Well, y2 and y4 are always going to be matching tables. If you look at every point on those tables, they are going to match. So that's going to give us answers of 1 and 3, which is going to give us choice C. As we move on to number 3, a population of Promisia, P, can be modeled using the exponential function P of t equals 3 times 2 to the t, where t is the number of days since the population was first observed. Which domain is most appropriate to use to determine the population over the course of 2 weeks. So domain, remember, domain is our input, which is usually x, but in this case is going to be our t values. So if they want to go first 2 weeks, and it says t is the number of days, well, 2 weeks equals 14 days. So if we want to cover our domain for the first 2 weeks, that means we need to go from 0 days to 14 days. In the fourth one, which one is not a linear function? Which usually means it's going to be exponential, and then we want to look for multiplying, percents, words like doubles, triples, and so on like that. A gym charges a membership fee of $10 down and $10 per month. Nope, that's linear. A cable company charges $2.50 initially and 3 cents per mile. Nope, linear. A restaurant employee earns $12.50 per hour. Again, linear. And then a car depreciates. Depreciates is usually a pretty good giveaway that it's going to be exponential, but also the key right there is a percent. When we start talking about percents, that's when we get into our nonlinear or exponential functions. Jill invests $400 into a savings bond. The value of the bond V of X in hundreds of dollars after X years is illustrated in the table below. Which equation and statement illustrates the approximate value of the bond in hundreds of dollars over the time in years? So if we look right here, obviously it is a growth function. So right then and there, we've got choice B and choice D are out. The next thing we're going to do is we're just going to plug in the fact that you can plug in each of these equations into your calculator then, or look at the fact that if you're less than 1, that means it decays. So obviously that one's out, and the only one that makes sense is choice C. So again, we knew decays was obviously wrong, but then here it said grows, but it was trying to sneak in. But if your parenthesis is less than 1, that automatically means it's going to be decays problems. That one's out. So the only one that says growth and then actually grows is choice C, because that parenthesis is greater than 1. And number 6, the population of 100 cells triples every hour. So which function represents? So remember, so this 100 right here is our starting value. And then if it's tripling, that's what's going to go in our parentheses for our pattern. So 100 right there is the start. Triples is our pattern or our multiplying number. And obviously t is our exponent. So which answer choice matches with that one? B. Marilyn collects old dolls. She purchased a doll for $450. Research shows that this doll's value will increase, so we know we are 1 plus 2.5% each year. Write an equation that determines the value V of the doll t years after the purchase. So if we do that, V equals our starting value of the doll was $450. It is 1 plus now 2.5%. If we make that into a decimal, we move our decimal place 2 spaces. That gets us 0.025. And then to the t. Or, okay, you could leave that exactly where it is, but just recognize that if you were to add the numbers together in the parentheses, they would mean the exact same thing. Assuming the doll's rate of appreciation remains the same, will the doll's value double in 20 years? So what we want to do is we want to plug in a 20 for our exponent. And let's see what we get. So if we go back to the main screen of our calculator here, we're 450 times 1.025 to the 20. And that gives us $737.30, and we'll round that to 38 cents, because remember, money can only go 2 places. So obviously it does not double. We now want to make sure we answer the question. So the answer is no, because and it says justify, it doesn't say explain. All right, so justify can be our work. Our work here shows that it only gets to the value of $737.38. On the day Alexander was born, his father invested $5,000 into an account with a 1.2% annual growth rate. Write a function, a of t, that represents the value of the investment t years after Alexander's birth. So, a of t equals 5,000 is that starting amount. Again, it's making money, so it's 1 plus. 1.2% as a decimal is 0.012, and then close parentheses to the t. To the nearest dollar, how much more is the investment will be worth when Alexander turns 32 than when he turns 17? So what we want to do is we basically want to find out how much it's worth when he's 32, how much it's worth when he's 17, and then we're going to subtract them. So if we do that here, we'll plug in a 32, and when we do that, we get 5,000 times 1 plus 0.012. Again, yes, you could have combined them, that's fine. So we get $7,323.97. So $7,323.97. So that's what it's worth when he is 32 years old. And then if we want to figure out how much it's worth when he was 17, we'll go back and plug in the same exact equation, but we'll change it to a 17. And we get $6,124.05. So again, it's the same exact equation, except now we're only going to be plugging in a 17. And we get $6,124.05. So if we want to figure out how much more it's worth, we'll subtract those two. So 7323.97 minus 6124.05. And it says to the nearest dollar, I believe. Yep, to the nearest dollar. So we get $1,199.92. $1,199.92. So the answer to the question is $1,200 more. If we keep going here and we take a look at our next, a car was purchased for $25,000, and research shows that the car has an average yearly depreciation, right? So that's usually a giveaway of decay rate of 18.5%. Create a function that will determine the value v of t for the car t years after purchase. So if we do that, we get v of t equals 25,000, because that's our starting point, times 1 minus, as a decimal, 0.185 to the t. Now I just want to show you this could also look like this, which is if we do our subtraction, we get 0.185 to the t. They mean the same exact thing. In part B, to the nearest cent, how much will the car depreciate from year 3 to year 4? So this is kind of like what we did before, where we're going to take our equation, we're going to plug in a 3, we'll get an answer. Then we'll plug in our equation. We'll get plug in into our equation with a 4 and get an answer. So if we do that in our calculator, it's 25,000 times 0.815 to the third. And again, money goes 2 decimal places, so we are 13,533.58. And then if we take that same equation and enter it with a 4 now, we get 11,029.87. So 11,029.87. So again, if we want to find the depreciation number, we're going to subtract those two. So 13,533.58 minus 11,029.87 gives us a depreciation number of $2,503.71. For our last one, the value v of t of a car depreciates, so again, we know it's decaying, according to the function v of t equals p times 0.85 to the t, where p is the purchase price of the car and t is the time in years since the car was purchased. State the percent of the value that the car decreases by each year. Now, everybody wants to say that we have an 85% decrease. But no, what that 85 really represents is that's the amount that remains. 85% of the value remains every year. So we have to be able to answer this question. 1 minus what gave us that 0.85? Well, in this case, it's 0.15. So that means is a 15% decay or decrease, okay? That number up top that's in the parentheses represents what remains. So therefore, we are going to have to figure out 1 minus what gave us that answer. In this case, 0.15. So that means 15% was the actual decay rate.